Okay, we're starting. So today, starting with chapter 5. Where we're going to do 5.1, integrals and antiderivatives. So at the beginning of the class, I spoke to you about sort of the birth of calculus. I mean, I know we've used it for a lot of applications so far, but sort of where it all started was with two main problems that we were concerned about and that were studied separately for a long time. There was the rate problem, figuring out how fast something's moving. We already know the main tool that we use to talk about that, the derivative. And the other problem was the area problem. So there's a so-called area problem, right? So the derivative was the answer to the rate problem, figure out how fast is this thing changing. Now we're going to consider the area problem, which is how much space is this thing taking up? What is the area or the volume of something, right? And the need for that kind of problem should a lot of times be obvious. If it starts, you can imagine someone owns a plot of land, they want to know exactly how much land they own. So that if the government is charging them property taxes, you're not overcharging me because I don't own that much land. How do you know how much land you own? Well, I measured it. How did you measure it? It has this weird shape. How do you know the area of that? If it's the area of a rectangle, if your land is exactly rectangular, sure, you can talk about the area. What if it has some weird shape, right? So the idea is, how do we figure out the area? And it can generalize to higher dimensions where we can talk about volume and stuff like that, but this is Calc 1, so we're just sticking with the 2D area of arbitrary shapes.
I thought it was applied calc.
For what?
You said it's calc 1.
Yeah.
But, okay, something.
The topics that we're doing is the standard topics covered in a Calc 1 class. We just don't go as deep. We mostly focus on the applications. Okay, so how do you find it of arbitrary shapes? And of course, often, so basically we start, and you guys might have done this, I guess, in some sort of maybe high school worksheets. Have you ever had that thing where they put something on a grid, they put the shape on a grid, and they ask you, oh, what's the area of this thing? And they dissect it like this, and they dissect it like that. And basically what you do is you like count up the rectangles, add up all the areas, and if there's something that's a part of a rectangle, you kind of estimate, well, that's about half of a rectangle. It's the same kind of idea we're going to be applying, right? So in order to figure out something for a general shape, we first figuring out the area under a curve. Right, that's how we start the process. So in the xy plane, let's say I have some function doing this thing, f of x. That's my y. How would I find the area under that curve? Right? The area of this is equal to what? Right? The idea being, I can create a shape by sticking it in between two functions. Right? Like an upper function and a lower function, and sort of figure out the area under this and the area under that, and I can figure out the area of this shape. So we figure out that, okay, we can talk about arbitrary shapes, but first let's just figure out how to do it for a single curve. So that was the idea. And the process is pretty much the same as what you would do here. We start by dissecting this shape into rectangles. So what we do is we take this function, doing this thing, and say we want to measure the area from A to B. What we do is we dice up the x-axis into subintervals. We create like the edges of a rectangle, and we create rectangles here. And basically we use the areas of the rectangles to approximate the area under the curve. And of course, the more rectangles you use, the more you fill in this space. So the more rectangles you use, the better the approximation becomes. That's kind of the idea. And the actual answer we consider it to sort of be like imagining that you have an infinite number of rectangles, right? So you sort of do this limit as you go to infinity kind of thing. You sort of apply calculus, the calculus idea to this process, okay? That one, because this is applied calc, we're not going to do the infinite case where we deal with infinite rectangles. I just want you guys to know the idea well enough to do it with a finite number of rectangles. So I'm going to give you a shape and I'm going to say use 4 rectangles to approximate the area under this curve, right? So how do we do that? There are several ways. I'm going to teach you several methods. We're going to look at 3 methods on how to do this. Very similar methods, but just how they're applied are different. So we're going to talk about 1, using right-hand endpoints. 2, using left-hand endpoints. And 3, using what we call midpoints. So in a question like this, I would specify to you a function and I'll tell you which method I want you to use, either the right or the left or the midpoint, and you would kind of break things up in the following way. So here's kind of the difference. Versus right hand, left hand. I'm going to have space for the middle. So here's the idea. I have some function. Let's say it looks like this. I want to approximate the area between A and B. One thing I can do is I can break up this interval into several sections. When I say I'm taking the right-hand endpoints, what I mean is that on each interval, I'm going to make the height of the rectangle be determined by the right side of the rectangle. So I take the right side, touch the curve, and wherever it is, I make that the height of the rectangle. So in this next one, I take the right side of the rectangle, touch the curve, and that tells me the height of the rectangle. Here, the right side, touch the curve, that tells me the height of the rectangle. And I keep doing that for as many subintervals as I need. Okay? Now notice here, it's not always the case, but in this case, it's of course going to be an overestimate, right? Notice that your rectangles actually cover the area under the curve plus a little bit more, right? So with this particular function, using the right-hand endpoints, I can get an overestimate for this curve. The curve is increasing, and that's why it gives me an overestimate. But this is sort of the idea. And I want to approximate the area under this curve using the area of the rectangles. I can look at the same curve between A and B. But the difference between a right-hand way of approximating the area and a left-hand way of approximating the area is simply that now on the interval, I let the left side of the rectangle determine the height. So the left side goes up, touch the curve, and that's the cutoff. Left side goes up, touch the curve, that's the cutoff. Left side goes up, touch the curve, that's the cutoff. Left side goes up, touch the curve, that's the cutoff. You'll notice here, the area of the rectangles would actually give me a larger answer than the area under the curve. In this case, though, the opposite sort of happens. There's extra space under the curve that's not covered by these rectangles. And this gives an underestimate in this. So So one thing gives you a larger answer than you want, one thing gives you a smaller answer than you want, and so what some people might think of being convenient is to actually, let's not choose the left or the right, but let's take the middle. Right? So if I look at A and B, let's say I cut this up into 4 as well, this defines an interval, but instead of taking the left or the right, I take the middle of the interval, I bring it up, and that determines where the height of the rectangle is. So I might put it across like so. Take the middle of the interval, that cuts off the rectangle. Take the middle of the interval, that's the cutoff for the rectangle. Take the middle of this interval, and that's the cutoff for the rectangle. And you notice in this case what's happening is it's a little higher than the curve on this side, but it's a little lower than the curve on that side. So we're thinking, when we do the overestimate, we also get a little underestimate with it, and so that kind of balances things out. And so in theory, in this case, this process, this might be more accurate than the other two. Right? Of course, as you're using an infinite number of rectangles, it actually doesn't matter which one of these you choose, they'll all give you the same answer. Right? So here's the idea is the following. Idea. Construct rectangles in one of the above ways. Approximate the area under the curve using the sum of the areas. Alright, so this is the idea. Let's actually make things a little bit more precise. By the way, in theory, we can get the exact answer using an infinite amount of rectangles. So you fill in all the gaps, and you're not spilling over, you're not spilling under. Amount is probably the wrong word to use there, whatever. It's not an English class. Rectangular amount of rectangles. Okay. And I'll talk about this case and what it means for us, but now let's focus on the approximations. So I want to make it a bit more specific.
Never mind.
I'm going to introduce some notation. Okay. So given this random curve f of x, I have a first point and a last point. This is A and B. These, I'm going to split it up into intervals. Right? And I'm going to label them with x's and subscripts. So A is normally x sub 0, while B will normally be x sub n. And I'll do a bunch of rectangles. Right? Dot, dot, dot. At the end of the day, I would end up with n rectangles. Now in this process, what I'm going to do is I'm going to take this interval and I'm going to cut it into equal spaces, right? So I'm going to want to take the interval AB and cut it into n equal pieces, right? So the length of any one piece would be what? take the interval AB, cut it up into n pieces, equally spaced, what would be the length of this?
1.
1 over n.
Huh?
F minus x over
Well, what's the length of this here? If I want to measure the distance here, this horizontal distance, what's it going to be?
b minus a.
B minus A. So I'm taking the length of B minus A, I'm dividing it into n equal pieces. So the length here is going to be B minus A over n. The notation for this is what we call delta x, or the change in successive x values. And with that, we can kind of do the formulas now. So, when approximating areas using n rectangles, we set delta x equals b minus a over n to be the length of each. We can call them subintervals. So I take the interval and I dice it into a bunch of subintervals. Equivalently, this is the width of the rectangles. But I know that to find the area of a rectangle, I need the length times width, right? Or the height. The height of the rectangle is given by what's the height of a rectangle given by? How would I determine the height of any one of these rectangles?
The y, the x of the point.
The y value, right? If I know if I'm taking the left or right side, I'll know what x value I'm plugging in. To figure out the height, I plug that into the function, and the height of that rectangle is just a y value. The height is given by f of x. So here's how I'm going to add up all these rectangles. So this means if we have a curve where this is x0, x1, x2, all the way down to xn, then we have the following, right? The right-hand approximation, which sometimes we call this big R little n, will be given by, I'm going to take f and evaluate it where? So let's say I'm looking at the first interval. What's the x value I'm going to plug in?
x1.
x1, right? Because I'm only looking at the right side. So I'm going to plug in x1 multiplied by delta x. That's the height times the width, plus x2 multiplied by delta x, plus dot 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 all the way down to the n, f of x n times delta x, because that's the right hand endpoint. And adding all these up actually gives me the area of all the rectangles. If I want to do the left hand, which is sometimes called Ln, right? So the left hand endpoints using n subintervals. What's the first guy I'm going to plug into f?
x0.
x0, right? So starting on the first one, the guy on the left is x0 times delta x plus f of x1 times delta x plus, what's the last guy going to be?
Xn minus 1.
Xn minus 1, the guy just before the last right endpoint. That's going to be n minus 1. If you use midpoint, it's big N, little n. This guy's called, we call it x1 star delta x plus da 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 f of xn star delta x. And in the above, the star just means in the middle, right? So x1 star is right in the middle between here. And x2 star is right in the middle between here, x3 star is in the middle between here. Where xi star is the midpoint. Between xi minus 1 and xi. And so that's how it is in principle. We can write this shorthand. One thing you can do is R, you can actually factor out a delta x and multiply by all the f's, f of x1 plus f of xn. Another way we can actually do this is to write, I don't want to scare anyone, but there's a symbol called big sigma, uppercase sigma, of f of x and times delta x. And you let your n number from 1, let's call it I number from 1 up to n. It's just a shorthand for writing this. This symbol just means add up a bunch of things that look like this, starting when you're plugging in 1 for I, then 2 for I, then 3 for I, then 4 for I, all the way up to n. Right? It's just a shorthand. We'll do some examples in a bit. I just wanted you to understand the theory of what we're doing here, right? So given an interval, given a function, and a certain number of rectangles, what you can do is you can cut this up into an equal number of spaces. The length of each space will be delta x, that is given by b minus a over n. The height of each rectangle would be given by the y value of the function that corresponds to which methodology you're using, right? So if you're using the right-hand endpoints, the height is given by the x values that when you plug into the function, the corresponding y values of the guys on the right side, right? Here, the heights are given by the y values that are corresponding to the x's on the left side of every interval, and the midpoint is the y values that are corresponding to the x values in the middle of every interval, right? You add these all up, you get the approximation for the area under the curve, and this is just a shorthand of writing all that. Now, again, to bring the theory, I'll do some concrete examples similar to what I would ask on a test pretty soon, but I just want you to have some ideas rolling around in your head. So now, in theory, the exact area under f of x on the interval AB will be given by, so these guys are all approximations for the area. This is going to be roughly the area A, right? But if I want to find the exact area, what we can do is we can have an infinite number of x values that I'm plugging into the y values, right? Make the spacing so small that I can plug in an infinite number of rectangles and add up an infinite number of things. And we're not going to get into the theory of how we know this works, how is that answer meaningful and all that. That's really something for non-applied Calc 1 class. But essentially the idea behind it is we're going to do, let the limit as n approach infinity, right? The number of rectangles you're taking, take an infinite number of rectangles up to this Riemann sum. It's called a Riemann sum, by the way.
That's a different symbol than the other one, right?
Huh?
Or is that the same symbol?
This is the same symbol as this. Right. This, by the way, is called a Riemann sum. I don't think I mentioned that. It's named after a mathematician called Riemann. This thing here is called a Riemann sum, right? It's just a sum of things.
That is very blue.
And we don't like writing down this all the time, so there's actually a shorthand for writing this as well. So whenever we're taking the limit of a sum of things that we're interpreting as the area under a curve, we write this symbol. It's an S, a very fancy elongated S for sum. We write the left endpoint on the bottom, we write the higher endpoint on the top, and we write the function f of x dx. Now, this is notation. Right, so whenever you see that, geometrically what you can imagine you're doing is I'm just finding the area under this function on the interval AB. And this guy, when it's in this form, it is called an integral. Right, so the title of the chapter is Integrals and Antiderivatives. We've just introduced the first star of the show. This is called the integral. It is just something that means the exact area under a graph, right? We write this symbol to mean we're cutting up a bunch of rectangles and we're making the number of rectangles go off to infinity. At the end of the day, that will be interpreted as the area under a curve, and we would write this to represent that area. Did you ever also write?
I was gonna ask, like, don't you need a plus C in there, or is that?
No, we're gonna get to that a bit later. Right, when we start talking about antiderivatives, we'll worry about plus C. This, by the way, is called, more specifically, this one is called a definite integral. The plus C comes in by what we call indefinite integrals, which I'll introduce a bit later. When A and B are specified, we call this a definite integral. A and B are called the limits of the interval. Okay, so I can say this is an integral, the limits are from A to B, right? A is the lower limit, B is the upper limit.
But are they like just the x, like, values, like the whole point of it?
Just the what?
Because like a is like x 0, 0, right?
Yeah, but they'll be constant. They'll be values on your interval. You can think of them as the endpoints of your interval. So the A is the left endpoint, the B is the right endpoint. If no limits are given, the symbol, this guy here, is called an indefinite integral. Not the current subject of our discussion, we'll discuss later. Okay. So we've introduced something that we call the integral, and its point is to measure the area under a curve, right? And basically the idea is dissect the interval into a bunch of things, erect rectangles that the height is determined by the curve in some sort of way, and then let the number of rectangles go up to infinity. You will get the exact area, and theoretically speaking, and we write down the symbol, the integral of f of x dx from A to B to mean that area. Let's actually just do some examples. We've done enough theory. Let's do some example, get some breathing room, and I'll give you some more theory. So here's an example. And I'll phrase it, the question will be phrased similar to this when I'm actually testing it. on it. So I would say something like, use Riemann sums with 4 subintervals to approximate the area under f of x equals x squared plus 1 on the interval 1 to 5 using, let's do a couple of them so you can see the difference. So let's actually do all of them. Right hand endpoints, left hand endpoints, and midpoints. Now, in general, I won't ask you to do all of them, but I just, since we're doing it in class, I want you to see all of them. But like on a test, I'd ask you to do one of them, right? And then I might ask you, is it an underestimate or an overestimate? So that's our goal. Approximate the area under x squared plus 1, y equals x squared plus 1, using 4 rectangles, right? Between the interval 1 and 5. So notice here, I can do a sketch. Let's do part A. Not necessary if I don't specify, but I think it's helpful. Graph looks like that. This is y equals x squared plus 1. From 1 to 5. So I can see that this is what I'm doing. And it says cut it up into 4 subintervals. So I'm going to cut that into 4 pieces. And I know I want the right pieces to hit. So this means delta x equals, what is delta x equal to? E minus a over n, which in this case would be what?
1.
It would be 1. So it's 5 minus 1 over 4. That's actually 1. So what that basically tells me is this interval is dissected in such a way that the spacing is 1 between all the intervals. So it starts with 1, and the next guy is 2, and the next guy is 3, 4. Let's see if we remember how to count, and 5. Right? So this guy here is representing my x0. This would be my x1, this would be my x2, this would be my x3, this would be my x4. Okay, so that's the situation. And so now, this means R4 would be equal to delta x times f of what?
F of 1, 2. Or
Well, R4 means we're taking the right hand endpoint. So what's the first x value I'm going to plug in?
2,
1.
2. Here's the first interval. Who's on the right side of that interval? 2 is on the right side of the interval. F of 2 is going to be the first y value. Then between 2 and 3, 3 is on the right. Between 3 and 4, 4 is on the right, 5 is on the right. So I'm literally taking 2, 3, 4, and 5. That's where I'm evaluating from. So it's f of 2, f of 3, f of 4, plus f of 5. And so that's going to be delta x is 1 times, what is f of 2?
5.
You're literally going to go back to the function and plug in x equals 2. So this is going to be 2 squared plus 1 plus f of 3, 3 squared plus 1 plus f of 4, 4 squared plus 1 plus f of 5, 5 squared plus 1. It's what?
48.
48. Okay. 48. That is an approximation for the area. 48 units. Whatever units I'm measuring my axes in, it'll be that units squared. So I'm saying the area under this is 48 squared units.
If that's, is this slightly over?
Yes, no, overestimate here. And it's not that the right-hand rule is always overestimate, I don't want to give you that impression, it's just that based on the picture, because this thing is going up as I move from left to right, the right side is always higher than the left side. And so we kind of have that going on. Right, so if you, to know whether it's overestimate or underestimate, the easiest way is probably to actually just sketch the graph and you'll see that the rectangles are higher.
I think it's 58.
My bad.
Okay.
Yup.
Also though, like
Yeah.
in general, is it safe to assume it's not too overestimated, or is it possible to be a very large overestimation or underestimation?
There's no way to tell in general. There's nothing that you can look at in the problem to kind of know. It really depends on the function. So obviously functions that change very fast, your estimates will be off by a lot more. Right? So if I'm looking at estimating the graph under x squared plus 1, sure I'll be off by a little bit, but if I do some like e to the x squared plus 1, that's exponential. The y value jumps a lot higher for each successive x value. So that guy's approximation would be off by more, and I would need more rectangles to get a better approximation. But there's no real way to tell in general how close you are, unless you actually find the exact area. Okay, but that would be an example. So if there was a problem on the test, that wouldn't say B and C. It says use Riemann Sum on 4 subintervals, compute the area under this with this and that. This will be what you write down. That's a full answer. Right? You're just taking length times width, and it really comes down to you figuring out what does my interval look like and which numbers am I plugging into the given interval. Right? So you figure out your delta x, that tells you the spacing. The first number in the interval, that is your a, which you can also define as x0, and this is your b, which is your xn, or in this case x4. And so you'd start with the a, and you jump by the spacing of delta x until you get to the last point. That way you'll know what numbers are available, and based on what the approximation is, you can plug in the guys on the right, or the guys on the left, or the guys in the middle. So let's actually do, and we don't even have to do this, but B, if I do 1 to 5, and this time I take the left side, it's going to look like this. Again, this would be 2, 3, 4. And so the left L4 would give me delta x times f of 1 plus f of 2 plus f of 3 plus f of 4. And I would stop there. I would not say f of 5 because 5 is on the right side of an interval. And I'm only looking at guys that are on the left side. So this one would go from 1 up to 4, whereas that one goes from 2 up to 5. So this is 1 times 1 squared plus 1, you plug into the function, 2 squared plus 1, 3 squared plus 1, 4 squared plus 1. And that's your approximation, whatever that is.
34.
And that would be the answer if you were doing left-hand intervals. How would midpoints change things? So if you do part C, let's use the midpoint. This is draw a picture here. So this is 1, this is 5. Your delta x is the same, b minus a over n, which is 5 minus 1 over 4, which is 1. So you start by first dissecting it according to the delta x anyway, but now you're going to start with your x1 star to be the guy that's in between 1 and 2. So how would I figure that out?
Divided by
Well, I know it's 1.5, but what if the numbers were weird?
Add both and divide by 2.
You find the average, right? So you can find the average, 2 plus 1 over 2. You get 3 over 2, which is 1.5. So that's the first guy that you would mark. Let me put that in a different color. So this is 1.5. And the distance between successive midpoints would also be delta x. So you can start at 1.5 and keep adding 1. So that'll be 2.5, 3.5, 4.5. Right? And now those are the numbers that I'm plugging in for my midpoints. So in this case, M4 would be delta x times f of x1 star plus f of x2 star plus f of x3 star plus f of x4 star. That was going to be slightly more annoying, but I mean on a test you have a calculator, it wouldn't be too bad. So it's 1.5 squared plus 1, 2.5 squared plus 1, 3.5 squared plus 1, and 4.5 squared plus 1. You add those together and whatever. And that would be your approximation. Yes?
Couldn't you get the answer for the midpoint by adding like the right hand, left hand, and dividing by 2?
Yeah, that's what I did here.
Okay. Oh.
But I did that for the first set, but then I just added
No,
one.
I meant the right hand sum and the left hand sum.
Oh, no, not in general.
No,
It would-
not in like every case.
No, that wouldn't in every case. It would depend on what your function is doing.
Gotcha. Okay.
So we got the idea? Like this is a problem type to approximate it using a finite number of rectangles. And I'll give you like 4 or 5. I'm not going to go beyond that. But based on whether I ask you about the right hand, left hand, or midpoint, you'll have to choose the right numbers. And so it just comes down to knowing how to set up your interval, knowing how to do this. I might also ask you, is this an overestimate or an underestimate, you think? And probably the best way to do that is to look at the picture. But there are other ways. So let me show you an interesting example. Coincidentally, it's going to be the same example that I used to introduce the idea of slope as speed, which is kind of foreshadowing actually to something called the Fundamental Theorem of Calculus, the connection between a derivative and an integral. Right? So it's somehow poetic that I'm using the same sort of example to motivate it. And it's not going to be something you can see in general, but the numbers are going to kind of say, hey, it's curious that the numbers worked out that way, and then we're going to investigate whether this works out in general, and it turns out that it does. So we had that thing where we had, there was a car traveling some sort of distance over time. I believe that we measured this in hours or something like that, and this was in miles. And we said at time equals 0, 0 it was here, and after there was 1 hour, there were 2 hours, it drove a distance of 80 miles. And then what we did was we interpreted the slope of this graph to be, it actually turns out to be the speed of the car. It was miles per hour, right? So the slope of this line turns out to be the speed or the rate of change of the position of the car. Now let's actually investigate what would the area be equivalent to. Let's say I take the area under this thing.
1/2.
What's the area here?
1/2 length times width.
Half base times height. And that would be what?
Is that an 80? Does that say 80 on the left?
Yeah.
Yes.
Okay, so it's 80.
What do you think 80 represents here? I mean, in the picture, it's painfully clear, it's just a straight line. But that number 80 is what? Where else did it appear?
Is this the hot
The
dog
line.
stand?
Huh? No.
Or the llamas?
This is the car driving
Ah,
at a constant rate of change. So I start at position 0, I drive at 40 miles an hour, I drive that way for 2 hours. What would 80 represent?
Distance, sorry.
The distance I've actually traveled. Also, what if I were to graph the velocity, right? So let's say I'm graphing here the velocity, or the speed, right? Since it's going to be positive. What would that graph look like?
derivative. The one on the left?
Well, what was the slope of this?
No.
It was 40, right? I think it was rise over run, it was 40. And it's a straight line, which means it has constant slope. So I'm just imagining there's a car here driving at a constant speed of 40. It's driving that way for 2 hours. And if I look at the area here, what do I get? It ends up being 80. In other words, the area under velocity is the change in distance. In other words, to use the notation that I had before, if I take the antiderivative, the integral of velocity, right? So v of t is representing my velocity function, right? This symbol finds the area under that curve between 0 and 2. Right? How you can interpret that, this was a t. How you can interpret that is the change in distance. Tell me what distance you were when you started. Tell me what distance you were when you ended. Subtract them, right? The same idea would sort of work even if I didn't start at position 0. If I shifted everything, the interval here would be shifted, the interval here would be shifted. It turns out that the area under this is, I can interpret it as a difference between this function. Okay? It's very curious. What is the connection between v and s? Remember s is the distance function?
Well, S is the distance function?
Yeah. So we know that if s is the distance or position function, what is v?
First,
It was the first derivative of s. That's how we got the velocity. In other words, I want to start introducing the notation now. I don't know if you were done with that. Basically, I said here the area under the velocity graph between 0 and 2 was the difference in positions. It turns out this works in general, right? I was going to prove it for you, but I don't think I want to do that anymore. So it turns out this actually works in general, right? V, this is the derivative of s. Right? So to go from s to v, you differentiate. It turns out, what if we wanted to kind of undo this process, right? What if we wanted to go from v back to s, right? I started out considering a question in terms of v, the answer ends up being in terms of s. So I'd want to go backwards. It turns out when you do that, it's called you're taking an antiderivative. So saying v is the derivative of s is saying S is an antiderivative. Of V. Right? So you can go forwards and backwards. I can differentiate to come here. I want to go back. We say I anti-differentiate. It's not always possible to do this, but we're going to look at cases where we can do this. Right? Not every function you can anti-differentiate. So here's where we're going to make the connection. Definition. Let f of x be a differentiable function, meaning a function that we can differentiate. Big F of x. We say big F of x is an antiderivative of little f of x if am I doing this in the right order? Because I'm using big F and little f. I'm also very sleep deprived. So big F is the antiderivative, means that the derivative of this is equal to that. Yes. Right? So I can say S is an antiderivative of V means that the derivative of S is equal to V. Yes. So that's just a definition. And that's the end of the definition. What we just illustrated, I'm not going to give you the proof, but it's not that hard to prove actually, is the following.
Shouldn't it be reversed? Shouldn't it be little f prime is f of x?
No, S is the antiderivative of V, right? So I can imagine that S is here. S is the big F, and V is the small f, and it's S prime equals V. It's in the right order. It's kind of going backwards from how you're usually thinking about things, so that's probably something causing confusion here. But at the end of the day, the following is what we want to get to. What we just illustrated is the following fact that, and this works out if f of x is continuous. Right? Because if there are gaps, bad things can happen. The antiderivative from a to b of this small function will be equal to big F evaluated at the upper limit minus big F evaluated at the lower limit. This is one part of a very important theorem. It's called the Fundamental Theorem. Of no less than all of calculus. It's that important of a breakthrough. Right? It's a theorem that comes in two parts. This is one of the parts. Right? So I think I mentioned this before, but calculus has been studied for like thousands of years. People have been doing things separately. We knew how to take derivatives, we knew how to take integrals. The reason why Newton and Leibniz are kind of credited as the fathers of calculus, when anyone asks who invented calculus, they sort of mention Newton and Leibniz, is because they were instrumental in coming up with this. They were instrumental in realizing, hey, these two things that we're all studying separately, they're actually like connected. Like they're two sides of the same coin. One is kind of connected to the other. Somehow me studying the speed at which something is changing is the same as me studying the area of under the curve in reverse, right? And that just, it wasn't realized for a long time. But the moment you realize that, like, a lot of things fall out of the sky. And we're not going to see all the things that fall out of the sky because this is Calc 1 and it's just, we're just at the end. But you go to like, I'm not going to see it. Yeah, but you'd explore a lot of the consequences of this theorem in Calc 2, Calc 3, and higher. It's a lot of it is based on this. It's on this theorem. So it's called the Fundamental Theorem of Calculus. But what it says you should realize is surprising. The area under a curve is somehow connected to the antiderivative of the function that you're finding. Somehow, doing the reverse of a derivative is the same as figuring out an area. Right? It seems crazy when you think about it, but it's actually, it's pretty straightforward, believe it or not. Turns out that you can, when you write this as a Riemann sum, you can actually simplify everything to get that. And it's just, the math just works out very nicely. And it's like, oh, well, that's interesting. It's probably not something anyone would have thought of unless they were studying a lot of the applications. Like, they're studying the speed of a car versus the distance it's traveling, and then they study the speed of this versus how much space this takes up, and they're like, hey, this is kind of curious how I'm getting the same numbers on the other side of the problem, and it's, you know, you can come up and figure this thing out. So this equation is actually a very important equation. It should be something that you should memorize. So this brings us to the idea, and this is the next star of the chapter, the antiderivative. So we already spoke about what an integral is. This is an integral. This function is called the antiderivative. So we're integrals and antiderivatives. Thus, it behooves us. I don't know. It becomes useful in knowing how to find antiderivatives. But the name is as it suggests, right? But as this suggests, we are just reversing derivatives. We're undoing a derivative. It's like if I tell you the derivative of a function, could you tell me the original function that I had before I took the derivative? That's kind of the goal. If you can find that, you can figure out the area under a curve. You can figure out the area under a curve. You can figure out many other applications, right? Look at all the applications that we did by figuring out how to find the slope of a straight line. Slope of a straight line, figure out how to do optimization, related rates. Like a lot of stuff come out of these simple geometric ideas. You'd be surprised, just being able to figure out the area under the curve, all the stuff that can lead to it, it's crazy. And so, it would be nice for us to be able to find antiderivatives. Meaning, how do you reverse derivatives? Right? So, example. If I ask you, what is the antiderivative of 2x? What would your answer be?
X squared.
Answer? X squared. But is x squared the only one?
No.
What else could be an antiderivative of 2x?
1 over x to the negative 1.
4x. No, just.
What if I took x squared plus 5?
Oh. Okay.
I differentiate that, the constant term goes away, and I end up with 2x again. Or if I take x squared plus 7,
Oh, that's the c.
right? It's the same thing, right? Whenever I have a constant, I differentiate it, the constant dies, so my antiderivative sort of has to have a placeholder for a constant. That's kind of why, I don't know if you noticed, but when I was writing the definition, I said an antiderivative. I never said the antiderivative, because there's not actually one. There's an infinite number, right? Because literally every time you add a constant, it makes no difference to the antiderivative, right? So we can say And here we kind of use the antiderivative of x squared of 2x is x squared plus c, where c represents some arbitrary constant. Now some of you might have seen the rules here. Yeah. Now some of you might have seen how to actually do that, but it turns out you don't have to think very hard to figure out things like that. All we need to basically do is figure out a way to reverse the formula. Right? There's a systematic way I could know that the answer was x squared, as opposed to me thinking of, because you differentiated this thousands of times, you kind of know that's the answer. What if you happen to see a function that you didn't differentiate it thousands of times? And I guess I'll give you all the other rules next time. I guess I'll just write it down and you think about it. Everyone's like, yeah.
Okay.
Turns out that was the rule that you can use, right? And you might notice that is actually reversing the power rule, right? The power rule says I multiply by the old power and subtract 1. Here I kind of do the opposite. I add 1 to the power and divide by the new power. It's just a way for me to reverse that power. This is called the power rule for integrals, and we'll see a lot of examples with it and talk about other rules.
Oh my god.